Okay, I hope I can hold this board here because this is really precarious for reasons I won't go into. The other thing we can see, just to kind of summarize this, for motion around a circle at constant velocity, and another thing we can verify here is that the magnitude of V is constant. With fear and trembling, I'm going to go over here and see if I can write that. The magnitude of the velocity is just pi over 4a, which is constant. So we're moving around the circle at a constant speed, and in this case, for this model, or for any motion around a circle at constant speed, it turns out that the A vector is perpendicular to the V vector, and there are all kinds of ways to argue that. And the more ways you know, the more you understand, and the more likely you are to someday use that in a profound way. Okay, again, I'm getting kind of hungry here. I think I said that V is perpendicular to the A vector and also to the R vector. And the component of the A vector in the direction of the V vector is therefore 0. So we have only a change of direction, and there's no effect on the speed. We don't need any force. We don't need to apply any force to make this happen. The only force we need is the force that keeps pulling the velocity toward the center. Yeah, maybe we need to apply that force, but that force does no work. That force is parallel to the A vector, has no component in the direction of the V vector, so the component of any centripetal force in the direction of motion is 0, and the centripetal force does no work, has no effect on the kinetic energy of the particle, no effect on the velocity. And we're going to see an example in a minute of very similar motion in a circle where the motion is not uniform. So we'll pick that up in a second as soon as I flip out a board here. Okay, I've written down a couple of initial ideas. We're going to let x of t this time be a whole lot like x of t was last time, except that the angle here, the argument of the cosine and the sine, is pi over 4t squared instead of pi over 4t. Now, that motion is still circular. You're still on a circle because if you add up the squares of these components, you're still going to get A. So you're still in a circle of radius A. Add up the squares, you're going to get A squared. You're going to find that the magnitude of x of t then is always A. The difference between the motion here and the motion in the example we saw just previously is that in that case the motion was at constant velocity, and recall it took a time interval of 8, whatever the time units are, to make a complete cycle. Here, the argument of the sine and cosine, which is the angle at which the point on the circle, well, the angle that the R vector makes with the positive x-axis measured in the counterclockwise direction, and you can verify that. And we just lost focus. Come back. Got to be careful how I move. Now I've lost the train of my comment, but this is the angle made by the R vector as measured counterclockwise from the positive x-axis, and this quantity increases faster and faster. You can see that just by doing a calculus analysis. The derivative of that function, there we go again, the derivative of that function is pi over 2t. The bigger t is, the bigger the derivative is, so the faster the value of pi over 4t squared changes, which means the faster the angle between positive x-axis and the R vector changes. So if we were to describe this motion by a set of points, those points would become increasingly further apart. I don't think I did a very good job of representing the characteristic. I don't know what's going on with that board. probably need to put a picture up here or something. Here until I need this part of the board. That ought to keep us in focus. Okay, and by that time I'll have enough on the board to keep the camera focused. Sometimes I wish I had control over the focus, but I don't in this case. Okay, so we're moving at a faster and faster rate across here, which tells us that our velocity vector is going to stay perpendicular or tangent to the curve, but it's going to get bigger and bigger. So right here is a set of velocity vectors. That's what we know just by thinking about the numbers. And by interpreting what we know about trigonometry and plane geometry, analytic geometry. Okay. Now our v of t is the derivative of our position function, and it's easy to take that derivative. Of course, we've got to, the chain rule, the derivative of the pi over 4t squared is pi over 2t. So we get pi over 2t, and we're going to get a pi over 2t over here, and we're going to have an a. I'm going to just go ahead and factor those out, and we get times the negative sign of pi over 4t squared I plus the cosine pi over 4t squared j. And you can work that out yourself. You should take that derivative. It's an easy derivative, very straightforward if you know the chain rule and the basic facts. And if you don't, you need to practice it. This is about as much as we need to know in this semester of this year of physics. Take derivatives of sine and cosine functions, and take derivatives of polynomials and power functions, all of which are very straightforward. But you do have to know the chain rule, so you need to review that. If you have that, you have enough computing calculus to do the computations in this course. And then if in addition your algebra skills are where they should be after a year of calculus, you're not going to have any trouble with most of the algebra, although it's real easy to get into some pretty hairy algebra. Okay. The acceleration function, we take another derivative. We're going to get another pi over 2t out of this. Keep that there, I can still write. We get pi squared over 4t squared a multiplied by negative cosine pi over 4t squared I minus the sine of pi over 4t squared times j. There's more to it. We've got to use the product rule, and that's just a bonehead thing on my part. As I say, it's getting toward dinner time. Brain isn't working too well. Okay, this is going to be part of it, but then we've also got to take the derivative of the pi over 2t and multiply it by the original function. And when we do that, let's take a chance and take this away. Okay, again, product rule. This function times this function, derivative of this function times this function is this function times the derivative of this plus the derivative of this function times this. This function is a pi over 2t, derivative of which is pi over 2. And then we multiply that by this original function. Okay, and then we can collect terms. Now let's digress for a minute and I'll probably pause the video and write down those collected terms. You don't need to watch me do that. You can do it yourself. You pause the video yourself and do that and see if you get the same thing I do. Let's go back up here. We can see that between one instant and a later instant that the velocity vector is going to turn toward the center, so we're going to have a centripetal acceleration here. So, if we take one vector and then another vector short increment later, that second vector is going to be turned, it's going to be tangent to the circle, so it's going to be at an angle that's rotated in the counterclockwise direction from the angle of the first. It's also going to be longer because, as we see, this thing's speeding up, so that our acceleration vector is no longer going to be perpendicular or approximately perpendicular to either of our vectors. It's going to have a component parallel to the average velocity vector, and it's going to have a component perpendicular to the average velocity vector. Okay, unlike the last model where we didn't have that perpendicular component. Well, okay, I'm going to pause here for a second and fill in this function here and just make a few connections.